Hello and welcome. Today, we're going to dive deep into a topic that is absolutely central to modern tablet manufacturing, directly compressible vehicles. Now, if you're in your final year of B-Pharm or you're an M-Pharm student, really getting a handle on these materials is going to be crucial for you. So let's get right into it. All right, so here's our game plan. First, we'll talk about why direct compression is such a big deal. What's the advantage? Then we'll get into the real heart of the matter, the vehicles that make it all possible. We'll look at them in practice, figure out how to choose the right strategy for your formulation, and then we'll tie it all together with a summary to make sure these key concepts really stick. Okay, let's kick things off with Section 1. Here we're going to lay the foundation, really define what direct compression is, and explore why it has become such an incredibly valuable technique in the pharmaceutical world. So, at its very core, direct compression, or DC as you'll hear it called, is really all about making things simpler and more efficient. It's a method where we just blend our active drug with all the other ingredients, the excipients, and press that simple blend straight into a tablet. Now, the key phrase, the part that makes all the difference, is without a prior granulation step. And this slide just illustrates that efficiency perfectly. I mean, look how simple that is. You blend and you compress. That's it. Now think about the alternative, wet granulation. That process has so many extra complex stages. You have to blend, then add a binder solution, then go through granulation, dry the whole wet mass, and then mill it down to the right size. And that's all before you can even think about getting to the tablet press. DC just cuts all of that out, which saves a ton of time, energy, and really importantly, it reduces the risk of damaging the drug with all that extra heat and moisture. So you might be asking, what makes this super simplified process even possible? Well, it all comes down to the vehicle. The right DC vehicle has to have a very specific set of properties. It needs to have excellent flow, right? That's to make sure the tablet dyes fill up evenly and consistently, especially on super fast machines. It needs high compactibility to form strong tablets that won't fall apart. And its dilution potential has to be high, which basically means it can handle a lot of drug loaded into it without losing its performance. These are the gold standards we're looking for. Okay, now for what is probably our most detailed section. We're going to explore the specific materials. These are the real engines of direct compression that have been engineered to have all those demanding properties we just talked about. You know, we can pretty much split these powerful excipients into two main groups. On one hand, you've got your single-component excipients. These are individual materials, things like cellulose or lactose, that have been physically changed or engineered to do the job. And on the other hand, you have co-process systems, which are way more advanced. They're these engineered particles that combine multiple ingredients to get synergistic benefits, performance that's way better than the sum of its parts. We have to start our tour with the undisputed champion, the real workhorse of direct compression, microcrystalline cellulose, or MCC. Seriously, if you've spent any time in a formulation lab, you've definitely come across this stuff. It's famous for its absolutely incredible binding abilities. What's so cool here is the way it works. Under pressure, MCC deforms plastically, kind of like clay. This creates a huge surface area for incredibly strong bonds to form, which gives it that high dilution potential we want. But it's not perfect. It can be really sensitive to having too much lubricant in the mix, and it can sometimes cause capping. That's when the top of the tablet literally pops off on very high-speed tablet presses. Next on our list is another classic, lactose. But for direct compression, we can't just throw in any old lactose powder. No, we use specially processed grades, like spray-dried lactose. It's been engineered to have much better flow and compressibility than the standard stuff. Spray-dried lactose gives you a really nice balance of properties. Its unique structure, a mix of crystalline and amorphous forms, gives you both good flow and good binding. It's a real staple for immediate release tablets. The one thing you, as a formulator, really have to watch out for, though, is the Maillard reaction. It's a chemical reaction that can happen with certain drugs, and it can lead to some nasty discoloration and even drug degradation. Just a quick but super important point about anhydrous lactose. By removing the water molecules that are normally part of its crystal structure, we get a material that's actually more compressible and much less sensitive to moisture. This makes it an amazing problem solver when you're working with an API that's prone to hydrolysis, breaking down in the presence of water. All right, let's switch gears and look at an inorganic option, dicalcium phosphate, or DCP. Now, the way this behaves under pressure is completely different from the plastic deformation we just saw with MCC. And that difference is exactly why it's so useful. The key phrase here is brittle fracture. Under pressure, DCP particles don't bend, they shatter.
This creates all these fresh new surfaces for bonding, which is perfect for high-speed tablet presses. It's also non-hygroscopic, meaning it doesn't soak up moisture from the air, which is another big plus for sensitive drugs. So what's the catch? Well, it's insoluble, so it can slow down dissolution, and it can be a bit abrasive on your press tooling over time.
Okay, last up in our single component category is starch. We're talking about specially processed pre-gelatinized starch grades that are designed to be multifunctional. They can act as both a binder to hold the tablet together and a disintegrant to help it break apart. So, as you can see, DC starch gives you decent binding and okay flow. Its real superpower is that it does two jobs at once. It helps form the tablet, and then, once it's in contact with water, it swells up and helps the tablet break apart. But let's be real, it's often not quite strong enough to do the job on its own. That's why you'll usually see it used as part of a team, often combined with something like MCC or lactose to get the tablet strength and powder flow you really need.
All right, now we're moving up to the next level of excipient technology, co-process systems. And I want to be clear, this is not just a simple powder blend. In this case, two or more excipients are actually fused together into one single engineered particle, often using a process like spray drying. The whole point is to create a super excipient, a material with synergistic properties that are way, way better than what you'd get from just physically mixing the same ingredients.
Considering how great MCC is to begin with, it's really no surprise that so many of these co-processed systems are built on an MCC framework. The basic idea is to take everything that's already awesome about MCC and then engineer solutions for its known weaknesses, like its mediocre flow or its sensitivity to lubricants.
And just look at how this plays out in the real world. Prosolve SMCC, for example, integrates colloidal silicon dioxide right onto the MCC particle itself, and that dramatically improves its flow. Or take Avicel DG, which co-processes MCC with dicalcium phosphate. Now you have a single material that gives you the best of both worlds, plastic and brittle deformation. Each one of these is a custom-built solution for a very specific formulation problem.
And it's the exact same story with lactose. It's another popular building block for co-processed systems. By combining it with other functional excipients, manufacturers are creating these ready-to-use all-in-one platforms that are perfect for direct compression. And this is where things get really amazing, the integration of functions. Look at something like cellulose, which cleverly combines the brittle fracture of lactose with the plastic deformation of MCC. Or go even further with a product like Ludipress. This isn't just a diluent anymore, it's a complete tablet-making system. You get your diluent, your binder, and your disintegrant all engineered into one single high-performance particle. It's like a one-stop shop.
Let's quickly touch on two more highly specialized categories. These are usually designed for one of the hottest areas in pharmaceuticals right now, orally disintegrating tablets, or ODTs. The ones that need to basically melt in your mouth in seconds. These advanced systems are precision tools for a very specific job. FMelt, for instance, uses a calcium-based to create a matrix that dissolves super fast. Then you have polyol-based systems like Ludiflash, which take advantage of mannitol's unique properties. It dissolves quickly and gives you that pleasant, cool feeling in your mouth. And they combine it with super disintegrants to create tablets that can literally fall apart in just a few seconds. Okay, so we've just looked at this incredible toolbox of materials that are available to us as formulators. So now, let's see how these DC vehicles are actually put to work to develop the different kinds of tablets we see out on the pharmacy shelves every single day. This slide really highlights just how versatile these vehicles are. For generic drugs, standard DC vehicles offer a really robust and cost-effective manufacturing strategy. For those sensitive APIs, being able to avoid heat and water is a total game changer for stability. When you're talking about industrial scale production, those high-flow materials are absolutely non-negotiable to keep the machines running at top speed. And for patient-friendly dosage forms like ODTs, those specialized co-process systems are simply essential. And this brings us to what is probably the most critical part of the process for any formulation scientist, making the right decision. We've got this incredibly powerful technique at our disposal, but when exactly should you use it? And just as importantly, when do you need to recognize its limits and choose a different path? So let's first map out the ideal scenarios, the green lights for choosing direct compression. When does this streamlined, efficient approach make the absolute most sense for your project? Okay, so direct compression should be your top choice when your early experiments show that your API already has pretty good flow and compressibility. It is a massive advantage for any drug that's sensitive to moisture or heat, since you get to skip the steps that introduce those things.
It's also the obvious choice when speed to market and cost are major drivers. And don't forget, those advanced co-processed systems can often help you overcome specific hurdles like sensitivity to lubricants. But let's be clear, direct compression is not a silver bullet. It has its limits. So what are the red flags? What are the situations where trying to force a direct compression formulation is just going to lead to headaches and failure, and you really need to consider a different technology?
This slide spells out those boundaries loud and clear. If your drug makes up a huge portion of the tablet, say a very high drug load, and it's also poorly compressible, a DC vehicle just won't be able to fix that. For very low-dose drugs, you often need granulation just to make sure every single tablet gets the exact same tiny amount of API. And for really tough APIs or super high-performance ODTs, you might have to accept that direct compression just isn't the right tool for that specific job.
All right, let's wrap things up by bringing it all together and summarizing the key take-home messages from our deep dive into directly compressible vehicles. These are really the core concepts that I want you to carry with you, both in your studies and into your future careers. So to boil it all down, direct compression is an incredibly powerful tool, and it's all made possible by this amazing portfolio of materials. But success is never guaranteed. It absolutely demands a smart, science-based approach where you, the formulator, intelligently match the perfect DC vehicle to the specific challenges presented by your drug and the goals of your final product. So let's end with a question to think about for the future. We've seen these excipients evolve from simple powders into these complex, highly engineered systems. As the entire industry starts to shift towards things like continuous manufacturing and faces new drug delivery challenges, you have to wonder, what comes next? What will the next generation of these essential formulation tools even look like? Thank you so much for joining this explainer.